Good morning. This is Professor Jitendra Kumar, and I will discuss today the new lesson named as property of pure substance. So first of all, before starting the different properties of these pure substances, we need to understand what is the basic definition of pure substance. Since as its name suggests that the pure substance is a substance having constant chemical composition throughout its volume. So since it starts with pure, so this the pure meaning of pure stands for constant chemical composition throughout the volume. So the pure substance is substance having constant chemical composition throughout its volume. Okay? For example, this water vapor is one of the best example of these pure substances. As you know that this example has been seen in daily life. Suppose that water having initial temperature of 40 degrees centigrade and it is boiled. As the heat is supplied to the water at constant atmospheric pressure, then what we observe that first of all the temperature of water starts increasing from 40 degrees centigrade to 100 degrees centigrade of water. So this is the first stage of heating in which the temperature of water increases but there is no phase change. So such types of heating process is called sensible heating process. Okay? And whatever heat is supplied during this process is called sensible heat. So what is the meaning of sensible heat? During sensible heating process, only temperature increases, whereas there is no change in phase. Okay? So as water starts heated, first of all temperature of water increases from 40 degrees centigrade to 100 degrees centigrade of water. If heating is continued, then what we observe here, this water having temperature of 100 degrees centigrade is converted into steam of temperature 100 degrees centigrade. So during this process, what we observe here, the temperature is constant but phase change. During this process of second phase of heating, what we observe here, this temperature is constant but phase changes. That is 100 degrees centigrade of water to 100 degrees centigrade of steam. So such types of heating process is called latent heating. Okay? So this latent heating, it is the process of heating in which temperature remains constant but phase changes. This is the next phase of heating. As water converts into 100 degrees centigrade of steam, and if it is still heated, in that condition the temperature of the steam increases from 100 degrees centigrade to further temperature. So once again, in this third phase of heating, what we observe here, the temperature of the steam increases but there is no phase change. So once again, this is the third phase of heating. During this third phase of heating, the sensible heating takes place. So if water is heated from 40 degrees centigrade to, suppose that 300 degrees centigrade superheated steam, in the first stage, this first heating process is sensible heating process. Sensible heating process, this is the process of heating of water from 40 degrees centigrade to 100 degrees centigrade of water. In this process, volume temperature of water changes but phase does not change. In the second stage of heating, what you observe here, this temperature of water remains constant, temperature of substance remains constant but phase changes. During this process, such types of heating is called latent heating, latent heat. During latent heating process, this only phase change takes place but temperature remains constant. In the third stage of heating, this as water converts into 100 degrees centigrade steam, if it is continued, then in that case, what we observe here, the temperature of the steam increases from 100 degrees centigrade to 300 degrees centigrade steam. So in the third stage of heating, this process is called once again sensible heating. So this is what we observe here. There are two types of heating process. First is sensible heating process and next one is latent heating process. In sensible heating process, in volume temperature changes but phase does not change, and in latent heating process this phase changes but temperature remains constant. Okay, so this is all about this heating of water from 100 degrees centigrade to 300 degrees centigrade steam. Okay, this is this conversion of water from 40 degrees centigrade to 300 degrees centigrade steam, right? So in this figure, just we are observing what we have explained here. This temperature of water initially is 40 degrees centigrade. Okay, if water is heated, it converts into 100 degrees centigrade of water. At this point, temperature increases, but state does not change. Still, it is water. If again this heating process is continued, then in process 2 to 3, this phase is latent heating, latent heat phase. In this process, during this process, this temperature remains constant, but phase changes. If heating is continued from 3 to 4, in that condition, what we observe that the temperature of the steam reaches to 300 degrees centigrade, but phase does not change. So this is once again this is the sensible heating process. So process 1 to T is sensible heating process, process 2 to 3 is latent heating process, and process 3 to 4 is sensible heating process. During this whole process, this pressure remains constant. At this line, 1, 2, 3, 4, at this line, the pressure remains constant. Okay, so this is the important observation what we have discussed here. In this figure, what we are observing here, as this pressure increases, because for this pressure, suppose that at particular pressure, let us suppose this is 1 atmospheric pressure, this latent heat is S3 minus S2. Suppose that this enthalpy at 3 is S3 and enthalpy at 2 is S2. So in this process, for this particular process, for the particular pressure, this latent heat is S3 minus S2. Okay, as this pressure increases, suppose that at this line, this pressure increases. As the pressure increases, what we observe here, this latent heat decreases. This value of this one, this S3 dash minus S2 dash, this value is less than that of this S3 minus S2. So what we observe here, as this pressure increases, latent heat decreases. Again, if pressure increases on this line, as we are observing here, as the pressure increases, in that condition, again we are seeing that this latent heat again decreases. And this is a trend, this one important trend follows that as this pressure increases, latent heat decreases. And at this critical point, what we observe here that at this pressure, latent heat is 0. So this is the critical point. This is the critical point. So with the increase in pressure, latent heat of evaporation decreases as this pressure increases. So with the increase in pressure, latent heat of evaporation decreases, and at the critical point, latent heat will be 0. Okay, so this is very important observation. We need to understand and we need to remember this concept with proper logic. Okay, so with increase in pressure, latent heat of evaporation decreases, and at critical point this latent heat of evaporation will be 0, right? In this diagram it is clear. Okay, in this next figure, in this figure just we are observing here that in this zone, since water starts at this point, at point 1, this temperature of water is 40 degrees centigrade, and at this point the state is water. So in this figure, in this zone, this water, this phase will be in water. Okay, so this phase will be in water form. Okay, so in this form, this is a liquid phase zone. In this zone, this is the combination of liquid and vapor. Okay, in this zone, under the dome, this phase will be in liquid and vapor, and outside this line, in this zone, this state will be in vapor zone. So in this zone, this phase will be in liquid form. In this zone, this phase will be combination of liquid and vapor, and in this zone, this phase will be completely vapor. Okay, this is important observation. Right. In this figure, what we are observing is that as the pressure increases, latent heat of evaporation decreases. So as we are observing here that this LH at pressure P2 is less than that of LH at pressure P1. We know it is clearly observed here that this P2 is greater than P1. So as pressure increases, latent heat of evaporation decreases. Right? In this figure, this is very interesting figure. This is on TS plot. So this is the dome what we have observed in previous figure also. The same dome is here. In this dome, this is the line. This is the line from this point to this point. This is the critical pressure. Okay, this is the critical pressure at which the latent heat of evaporation was 0. So from this line to this line is called saturated liquid curve. This curve is called saturated liquid curve. Right? And from this point to this curve, okay, along this curve, this is saturated vapor curve. So from this critical point, this curve is called saturated vapor curve, and from this point to this curve is called saturated liquid curve. Okay, so in this zone, liquid in subcooled form, this is the liquid in subcooled form. At this line, at this curve, the liquid will be converted into saturated liquid. Okay, in this zone, this is the combination of liquid and vapor, and at this point this converts into vapor, and vapor will be in saturated form. And from this, apart from this curve, this will be superheated zone. Okay, so there are 3 zones. Subcooled zone, this is saturated liquid curve. At this point, this liquid will be completely saturated. This is the zone of liquid and vapor. At this point, this vapor will be saturated, and apart from this curve, this vapor will be superheated. So basically what we are observing here, this curve is called saturated liquid curve, and this curve is called saturated vapor curve. Right? So this is the same dome is drawn here. So we need to understand some different words, some different terms like degree of subcool and degree of superheat, right? So as we know that this is the subcooled region. This is the subcooled region, right? In subcooled region, the temperature of fluid will be less than that of saturated temperature, because this is the curve of this saturated liquid curve. So at this point, this temperature is called saturation temperature. Okay, so this is the initial point, initial temperature of water. Suppose that it was 40 degrees centigrade in our previous discussion. So this, as this temperature of water increases to 100 degrees centigrade, this temperature will be called as saturation temperature. Saturation temperature of water at 1 atmospheric pressure is 100 degrees centigrade. So in subcooled region, this is the subcooled region. In subcooled region, this temperature of water is less than saturation temperature. Okay, because as saturation we know at 1 atmospheric pressure the saturation temperature will be 100 degrees centigrade. So in subcooled region the temperature of fluid will be less than saturation temperature, and during this process of heating, because the initial temperature of water is T1 and saturation temperature is Ts, so this temperature difference, this Ts minus T1, is called degree of subcooling. So during sensible, okay, this Ts minus T1, this Ts minus T1 is called degree of subcooling. Okay, because this is subcooled zone, this Ts minus T1 is called degree of subcooling, right? This is superheated zone, right? So this is still at this whole, at this complete line, along this line this temperature of fluid will remain constant. So this is the superheated zone. So in superheated region the temperature is greater than saturation temperature. Okay, so in superheated region the temperature of fluid will be greater than this saturation temperature, right? So degree of superheat will be difference of T2 minus Ts. So T2 minus Ts is called degree of superheat. So this is important, degree of subcool and degree of superheat. This Ts minus T1 is called, difference, temperature difference is called degree of subcool, and this T2 minus Ts, this temperature difference is called degree of superheat. So this is very important and very easy to understand. This is subcooled region, this is superheated region. Okay, right? Degree of okay. Next term is dryness fraction. Next term is dryness fraction. We know that in this zone, it is discussed in this zone, since it is the wet zone. This zone is called, in this zone, this is wet zone. That wet zone means this will be combination of liquid and vapor in this zone from this point to this point. At this point this is saturated liquid, at this point this will be saturated vapor, and in between these points, from this point to this point, the state will be in vapor phase. Okay, so this is a combination of liquid and combination of liquid and vapor. As temperature increases, this composition of liquid will be decreasing and it converts into vapor form. And at this point, just we need to understand very clearly, at this point the liquid in saturated liquid form. At this temperature this liquid is completely saturated. There is no part of vapor at this point, because liquid in saturated form, there is no part of vapor. At this point this mass of vapor will be zero. Only mass of liquid will be there, only liquid part will be there. As this latent heat is added, this composition of liquid will start decreases and composition vapor will start increases along this line. And as this line moves ahead, at this point, since this is the saturated vapor point, so at this point the liquid part, mass of liquid part will be zero, and mass of vapor part will be only in this portion, only vapor part will be there. There is no mass of liquid. Okay, so at this saturated liquid point, at this point this is a saturated liquid point. So in that condition, this mass of liquid part will be there, mass of vapor part will be zero, and at this point this is complete vapor form, so mass of liquid part will be zero. Okay, in this zone, this is called wet zone. This is the combination of liquid and vapor. right? So first of all, we need to understand this mass fraction, this dryness fraction. This one important term is here, dryness fraction. Dryness fraction, as we know that in wet zone, this is the combination of liquid and vapor. So dryness fraction is the ratio of mass of vapor to the total mass. This total mass, what is the total mass? Total mass is the mass of liquid plus vapor. And this dryness fraction, this is the ratio. So this dryness fraction defined as it is the ratio of mass of vapor to the mass of liquid and vapor. This is written here. It is defined as the ratio of mass of vapor to the total mass of mixture. This is mass of vapor. Total mass of mixture is mass of liquid plus mass of vapor, right? Okay. This is very important terms here. The dryness fraction, okay, because this is the dome we have studied. So this is the original dome. Outer side dome is, okay, right. At this dome, at this point, just we need to find what is the value of dryness fraction. The dryness fraction is represented by X. Since this dryness fraction is ratio of mass of liquid divided total mass of mixture. Okay, total mass of mixture is equal to mass of liquid plus mass of vapor. Let us suppose we have to find the dryness fraction at this point. Since at this point this mass of vapor is 0, there is no parts of vapor at this point. So in that condition, this dryness fraction will be mass of liquid by mass of liquid plus mass of vapor, which is 0. Therefore, this mass of vapor, there is no content of this vapor part at this point. So in that condition, this dryness fraction will be 0. Okay, as we move from this point, since dryness fraction value increases, because in this condition this mass of vapor part will start increases. As this latent heat is added, this mass of liquid part decreases and the mass of vapor part increases. So in that condition, as we move from left to right, this dryness fraction will be increasing. And at this point, since there is no liquid part, so in that condition only vapor parts will be there. So at this point the dryness fraction will be 1, because we know that X is equal to mass of vapor divided mass of liquid plus vapor, and at this point this mass of liquid part is 0, so this will be mass of vapor divided by mass of vapor, so this dryness fraction will be 1. So what we observe that this dryness fraction lies between 0 and 1. Dryness fraction lies between 0 and 1. At the saturated liquid curve, along the saturated liquid curve, the dryness fraction will be 0. Why? Because along the saturated liquid curve there is no vapor part, so dryness fraction will be 0, because we know that this dryness fraction is the ratio of mass of vapor to the total mass of mixture. Since there is no parts of this vapor, so in that condition this dryness fraction will be 0. The dryness fraction along the saturated vapor curve is equal to 1, because we have observed here, since along this curve, since there is no liquid parts, so in that condition the dryness fraction will be 1. So dryness fraction starts from critical points, because along this curve this dryness fraction is 0. So this dryness fraction starts from critical point, right? This is all about this variation of dryness fraction, which varies from 0 to 1. So at saturated liquid curve, this dryness fraction will be 0, and at saturated vapor curve, this dryness fraction will be 1. Right? This is all about the pure substances, description about this pure substances. Right? So first of all, in this videos, just I am summarizing what we have studied in these videos. First of all, we need to understand this definition of pure substances. So this pure substance in the substances having constant chemical composition throughout its volume. So this is called pure substance. Now this is example of this water vapor mixture. This is the example of this pure substance. In next discussion we will try to understand what is the meaning of sensible heating and latent heating. In this example we have studied that we have seen that during sensible heating only temperature change whereas phase does not change, and during latent heating this temperature remains constant but phase changes. This is the second important observation point. Third important observation point is as pressure increases, this latent heat of evaporation decreases, and at critical point the latent heat of evaporation will be zero. This is our third important observation point. Next important observation point is this some zone we have seen that there are two parts of curve, the left portion of curve and this is the right portion of curve. This left portion of curve is called saturated liquid curve. From this critical point the left portion of curve is called saturated liquid curve, and this right portion of curve from this critical point it is called saturated vapor curve. This is the third important, this is the next important observation we need to understand. From this critical point the left portion curve is saturated liquid curve, and from this critical point right portion of curve is called saturated vapor curve. There are three zones. This is liquid zones. First one is the liquid zones. From left hand side of this saturated liquid curve is called liquid zone. Within the dome this is the wet zone, and from the right portion of this saturated vapor curve is called superheated zone. There are three zones: liquid zone, wet zone and superheated zone. Okay, this is our next important observation. Third point is next important observation point was degree of subcooling and degree of superheat. Since this in subcooled region temperature is less than saturation temperature, so at this temperature difference Ts minus T1, as we have studied in this previous slide, slide, just to revise, you may go through this previous slide. This Ts minus T1 is called degree of subcooling, and degree of subheating, superheating, that is whatever temperature, the maximum temperature, this is T3, this T3 minus Ts is called degree of superheat. Right? Next important point is dryness fraction. Dryness fraction is the ratio of mass of vapor to the total mass of mixture. This is the called dryness fraction. Is dryness fraction we have seen a next important observation point is that we have seen that this dryness fraction varies from 0 to 1 along the saturated liquid curve. Since there is no vapor parts, in that condition this dryness fraction will be 0, and along the saturated vapor curve, since this mass of liquid part is 0, only vapor portion part is there, therefore in that condition this dryness fraction will be 1. So the dryness fraction will be varying between 0 to 1. Okay, so at saturated liquid curve this dryness fraction will be 0, and along the saturated vapor curve this dryness fraction will be 1. Okay, this is our important observation points what we have studied in this session. Thank you. All the best.